Hi, this is part 3 in a series on pump head calculations. This is pump head terms number 2. And you'll need to know this stuff if you're writing your third class B1 exam. It's in chapter 13. So if you haven't seen part 1 and 2, you might want to start there first. Otherwise, we're going to keep on moving. So what we talked about in the previous section was Bernoulli's system as it applies to pump systems. And so we had Bernoulli's equation, and we know that it's sort of long and complicated, but if we break it down, so if I was to rearrange this and just group the different terms together, what I could end up with is something like this. So I've moved the V1 from the left-hand side over to the right-hand side and all the other applicable terms. And so really what I have is just from two different points, a number of different components. And in the last video, we talked about static heads. So those are my Z values. We have also a couple other terms that we use. So the pressure over density times gravity is what I consider to be my pressure heads. I have velocity heads, which are the velocity squared over 2g. And then I also have another term which I use to describe losses. We talked a little bit about pressure head earlier, so let's just talk about what pressure head or where that might come to be. So in the previous example, what we'd assumed was that our tanks were open to the atmosphere. Okay, so when we did static heads. So if we have a vented tank, yes, we'd assume that pressure was 0 gauge in both of those tanks. And so really there was no pressure that was pushing against either of those surfaces that was influencing what our pump had to produce. However, if we don't have that, so we have a pressurized tank either on the reservoir side, on the inlet side, or the outlet side, then we're going to need to take into account the pressure in our system. So if we have a pressure 1 or 2, that's going to mean that we're going to have a pressure head that exists inside of that system. So we'll have to consider that as we go through our calculations. Let's take a look at how we would calculate pressure head. So let's say we did have a tank and it was pressurized to 600 kPa. System contains a fluid with a relative density of 1.2. What's the pressure head created by this pressurized tank? So really, how much height of water would be produced if we were able to make use of all of that pressure just to lift water up into the air? Okay, so here's where we'd have to start. We'd have to figure out our density. So the relative density, 1.2 times 1,000, gives us a final density of 1,200 kilograms per cubic meter. And then we could punch that into our pressure head calculation. Now remember that we want to make sure we're in our base units. So for pressure, that would be pascals. So when we punch into our pressure head calculation, make sure we're switching over to pascals. So 600,000 pascals over 1,200 kilograms per cubic meter times gravity. And we would end up with a pressure head in this case of about 51 meters. So that pressure that's inside the tank could produce a column of water that was about 51 meters high. Okay, so now that we have an idea that pressure inside of a tank creates an equivalent column of liquid, let's see how that compares to our thoughts on static head. So previously we talked about static head being in tanks open to the atmosphere. And when we considered that, we only considered the static head to include the height of those fluids. So depending on the height of the inlet or the discharge, it would affect how much static head we had. And so we just did a calculation to say the height difference between those two columns would allow us to calculate our total static head. However, once we add in the idea that a reservoir could be pressurized, that pressure comes with an equivalent column of fluid. And so when we calculate a static head with pressurized tanks, what we want to do is include the pressure that might exist at either of the tanks as an equivalent column that's going to add to our static pressures or static heads. So for instance, if we were finding our total static head, instead of just being Z2 minus Z1, what we would also have to do is include in the pressures. Now we want to be careful to add pressure or subtract pressure depending on which side of the system it's on. So if we take a look at what that might look like on a head basis or energy basis, we have a few different components now. So instead of just the vertical heights, what we might have would be, in this case, say we had a Z1 value which was contributing to some energy at that point 1. And we also had a pressure, so our pressure over rho g was going to contribute some amount of energy. And if we consider what happens at the other side, so we have our point number 2, we're going to have a larger amount of energy in the form of static head, the Z2 value. And then, who knows what we have for our pressure at number 2, but we've got pressure 2 over rho g. So you can see somewhere along the line, we've increased in the total amount of head and the difference between these two. So the difference here would be really our total static head, considering the pressurized tank. The other term that we introduced there was velocity head. And velocity head, in the previous examples, we made the assumption that when we have the top surface of a tank or reservoir, it's a large surface. So there really is no velocity either downwards or upwards at those surfaces. So we had kind of assumed that velocity was 0. However, if we don't have 0 velocity, then we'd need to account for it. And here's a couple cases where that may happen. So maybe on our discharge, we have an open pipe that discharges to a tank. Well, at that point, we would have some velocity of that fluid leaving the system. And we'd have to account for our velocity head. The more likely scenario that you're going to come upon in your exams would be that we have a piece of piping and we need to consider a velocity moving through that. And so in this case, if we were considering a section of piping, either leading into the pump or leaving the pump, we'd have to consider the velocity head in that case. Okay, so let's just do a quick calculation on calculating our velocity head. So let's take from our previous example there. We have water, it's 3 meters per second, and it's moving through a 3-inch pipe. What's the velocity head created by that moving fluid? So essentially, how much energy does that fluid have in terms of a column of water equivalent? Okay, well, we know that our velocity head is v squared over 2g. And if we punch in our 3 meters per second squared and then divide that by 2 times gravity, we would get, in this case, velocity head 0.46 meters. Okay, so let's figure out how all this applies to pumping systems and figuring out pump performance. Okay, so here's a pump manufacturer that I found off the internet, and I've selected a pump that they would supply. So a couple things that I want to take note of is that when we talk about pumps and we specify pumps, we can see that we have a flow rate. So you can see the max flow for this pump, 300 cubic meters per hour. But what it doesn't specify is what pressures it delivers. Okay, what it specifies is max head of 80 meters, okay, or else my imperial equivalent. So this pump has specified for us how much head this pump can produce. So when we talk about pumps, we're talking about head. Now, if we look at a little more detail for this pump, I could pull up a data sheet. So the manufacturer provides a data sheet for us. Okay, so this is a performance data sheet for this pump. And the pump provides us with different outputs. So we look at the X axis, and what it tells us is the output of the pump. So we can see it has its capacity, and it's anywhere from 0 to 300 cubic meters per hour. The other side, the y-axis, what it tells us is total dynamic head. So that's telling us essentially the output or the amount of energy that it can impart into the fluid, but it doesn't tell us in pressures, it tells us in head. So we have a case where this pump could produce up to 70, 75 meters worth of head. And we note that it's not just head, it's total dynamic head. And I guess we got to start figuring out what some of these definitions would be for different heads that we may see. So when we talk about dynamic heads are going to include all of the heads. So we've talked about some velocity, pressure, and static heads, as well as accounting for any losses in our system. And we have 4 different dynamic heads that we're going to talk about. So we have dynamic suction head and dynamic suction lift. Those ones are related to each other. We have a dynamic discharge head, and then we have total dynamic head. And so we can see on that pump performance curve, total dynamic head is sort of our endpoint. That's the endpoint for all of this. Okay, let's take a look at dynamic discharge head. So this is on the outlet side of the system. Okay, so the outlet of the pump is where we would start to the final destination for our fluid. Really, it's a measure of how much energy or how much head we must have in order for fluid at the pump to be able to make its way all the way to the final destination. And just like we had with our dynamic suction head, dynamic discharge head has a direct relationship to the pressure at the outlet of the pump. So the higher the pressure at the outlet of the pump, the higher the dynamic discharge head. So if we talk about our calculation to get our dynamic discharge head, let's start again at the same place we did before, Bernoulli's. So in this case, I have 1 at the outlet of the pump and 2 at the surface. And I can eliminate some of these terms. My height of my pump, Z, is going to be 0. Once again, in between 1 and 2, I don't have a pump. And if my tank is sufficiently large, I can assume that my velocity at 2 is going to be 0. So I've eliminated, once again, 3 terms out of Bernoulli's. I then simplify that a little bit and rearrange, and I get a similar calculation to what I did before with my dynamic discharge, suction head. The pressure at 1, which is what I consider to be my dynamic discharge head, so the pressure 1 over rho g is equal to the static discharge head plus the dynamic pressure head plus the losses minus the dynamic velocity head. Now, I'll caution you that some of your textbooks may have an error with this calculation. So some of them will have a plus dynamic velocity head, but it should be a negative value. It should be a negative value in our calculations. So dynamic discharge head is really a measure of how much energy this fluid needs to overcome all of the obstacles in the way of getting to my final destination. So in order to push water up to number 2, it has to overcome the height gain to number 2. It has to overcome the pressure that might exist in the tank at number 2. It has to overcome the friction losses on that pathway. But it also carries with it some energy as it leaves that pump. So it carries that velocity with it. So that is a benefit to me. It's some extra energy that I can account for at the end. And that's the reason why we have the negative there. Okay, so I'm going to take a look on an energy basis at the dynamic discharge head. So I have an outlet at my pump number 1, and it's going to feed to a tank number 2. And in this case, I'm going to consider the movement of fluid from 1 to 2. So when we consider our energy, when we're at number 1, we have no head, so no static head, so Z1 is equal to 0. We have a velocity head, so whatever's leaving that fluid is going to be creating a head. And we also have some sort of pressure head, so that's essentially what we're considering as our dynamic discharge head. Now at my outlet, as I move from 1 to 2, we have a few things that are going to change. So first of all, my total amount of energy is going to drop because of friction. So as I move through my system, I am going to have some losses in friction, which means that my total amount of energy is, some of it is lost. So I have a head loss that exists. My Z value increases as that goes up in height. And I have a pressure head that exists. So that would be my Z2. And then I don't have a velocity component because it comes to rest at the surface of that tank. Okay, so what I'm left with is a number of different energies. And what I'm trying to solve for would be this pressure, essentially. And so if I think about how I could solve for that, if I look at my system, well, my pressure is going to be the value of those 3, which is going to move me up to this top line. And then I'm going to subtract the velocity component over here. And what I should be left with is the height equivalent to that pressure. So in equation form, what that looks like is my, essentially the dynamic discharge head, so the P term, which would be P over rho G, P1, is going to be equal to Z2 plus P2 over rho G plus my head loss minus my V1 squared over 2G. And as we take a look, that's equivalent to the equation that we came up with. So sometimes it's easier for us to see that on sort of an energy map like I've just drawn there. As we move from one side to the other, we can come up with our equation for dynamic discharge head. So our dynamic suction and head lift is where we're going to start. And as we can see, this is really a measurement of what's happening on the suction side of the pump. So So what is happening on the pathway into the pump? Dynamic suction head is our normal case, the upper case. The dynamic suction lift would be the case where we have that reservoir or the water level is below the pump, so it has to pull that water upwards in order to make it to the pump. So they're very similar. They're both talking about the inlet side, but we have often two cases. Either we're drawing water down from the reservoir to the pump, or we're pulling water up to the pump. And then we have either suction head or suction lift to describe those two. The way we can think about what this really means is dynamic suction head or lift. It's how much total head is going to be supplied to the inlet of that pump. So factors such as the pressure in that tank is going to help push water into that pump, or the static height is going to help push water into that pump. And so the dynamic suction head is a measure of really all of the factors that are either helping to push water into the pump or preventing water from making its way into the pump. And one thing that we can note is that dynamic suction head or lift has a direct relationship to the pressure at the inlet of the pump. So if we were to read a pressure gauge at the inlet of the pump, it would give us an indication how much dynamic suction head there is available. The higher the pressure at the inlet of the pump, the more dynamic suction head that we have. Okay, let's take a look at it in terms of Bernoulli's equation and then come up with a calculation for how we would find dynamic suction head. Okay, so here's our version of Bernoulli's equation. So we have our velocity head, our static head, our pressure head at number 1, plus whatever a pump energy or head may provide into our system, minus losses, so friction and other losses. And that's going to be equal to the velocity head, the static head, the pressure head at the second point in our system, so the downstream point. But we know that we can eliminate some of these things. So for instance, if we have a large enough tank, we can assume that the velocity at 1 is 0. Because we're not passing through a pump from 1 to 2, we don't have any head that the pump is either producing or removing. And if we assume that our baseline point, the height, the static height of the pump is at our lowest point in our system, we can assume that that is 0. Okay, so we've eliminated 3 terms out of Bernoulli's, and if we rewrite that with those missing terms removed, we've got another line. But in order for me to find out what my dynamic suction head is, remember that it's related to the pressure at the inlet of the pump. So that would be my pressure 2. And so if I rearrange that to solve for my pressure 2 term, or my pressure head at the pump, what I get is pressure 2 over rho g is equal to my Z1 value plus the P1 over rho g minus my losses minus my velocity head. And so we have a whole bunch of sort of equations if we break that out from Bernoulli's equation. And if we write it out just in terms of what they are, we have dynamic suction head. It's going to be equal to my static suction head plus my static pressure head minus my losses minus my static velocity head. So we can think of it this way. When I look at what happens to that pump, what pressure is available to it or what head is available to it, it's going to be influenced by the pressure that's in the tank. The more pressure in that tank is going to help push fluid to the pump. The height of that fluid in the tank is going to also help influence how easy it is to flow down to the pump. But that's kind of all the energy that I'm going to start with. And that energy also then goes potentially to two places. One, we could lose some because of losses, or else some of that energy could be converted to velocity through the fluid. So it sort of disappears in terms of pressure that's available at the pump. So we have a calculation for our dynamic suction lift, and we've got 4 factors. Some of them we add, some of them we subtract in order to get there. We also can take a similar approach if we look at the energy side for dynamic suction head. That's a good example for one to look at. So if we start at number 1, what number 1 has is, well, we've got some Z value and we have some pressure in that tank. Okay? We have no velocity. It's going to be a still surface. Okay? And then if we move our way to number 2, well, because we have flow that moves through this pipe, we're going to have friction. And so the total amount of energy in our system is going to drop because of the losses. Okay, so as we get to number 2, we have some sort of head loss. And what's available at number 2? Well, we don't have any height, so no Z term, but what we do have is going to be some pressure. So pressure 2, so that's leading to having a head. And as well, we're going to have a velocity term. So we have our velocity 2. And so if we look at how do we come up with our pressure 2, well, it's going to be the distance to get me up on the left-hand side, P1 plus Z1 terms. And then I'm going to subtract the head loss and the velocity. So what I would end up with is P2 over rho G is equal to my pressure 1 over rho G plus my Z1 minus my head loss minus my V squared, I guess that's V2 squared over 2G. And what we can see is that that mimics the equation that we came up with in our discussion. So we have our dynamic suction head for that point, and it matches up from our energy perspective to what's happening in our system. Dynamic suction lift is similar to dynamic suction head. The only difference is that now we have our water reservoir is below the pump. So it causes a little bit of confusion, I guess, with how we come up with our equations, and we'll walk through that here. So we're going to start out the same place. We have 2 points, 1 and 2, and we've got, I guess, our Z1, we'll set it as our lowest point, and that moves up to our Z2 value. And so based on that, we can start eliminating some of our terms out of Bernoulli's. So no velocity at the tank at 1, no height at 1, and we don't have a pump in between 1 and 2. So we can eliminate those terms. And that leaves us with 5 terms left. And if we rearrange these, we could set it so that we have our P2 term is the one that we're solving for. And you can notice that we have a whole bunch of negative values, negative Z, negative losses, negative velocity. And generally when we have a pump that has a supply that's below it, what it's going to have is a negative head leading into that pump. We have less than atmospheric pressure usually because that pump has to provide quite a bit of suction to lift the water out of that reservoir. So because P2 is usually going to end up negative, the sort of the common thing that happens in industry is when we say we talk about lift, we talk about the amount of lift as a positive amount. So the amount of lift that pump needs as a positive amount. And really what that means is we just multiply this whole thing by -1. So we've swapped the signs for all of our pluses and minuses. So if we multiply that by -1, what we get is that dynamic suction lift term equal to now a bunch of positive values with only one negative value. And if we make their short forms, dynamic suction lift is going to be equal to the static suction head plus the losses plus the velocity head leading into the pump minus the pressure head. The pressure head being the only thing that's really going to be helping this in terms of energy going into that pump. Now you'll get a value of, for your dynamic suction head, that's going to be a positive value based on this, but we want to be careful that we call it a lift because it really is a negative value. Confused? Yeah, it's a little confusing. So be careful with dynamic suction lift and how it's approached. So we saw in that pump performance curve that we cared about the total dynamic head. So we've talked about the suction side, we've talked about the discharge side, and total dynamic head is really a measurement of the change ahead across that pump. So if we have a pump and we see that we have a pressure change across that pump, and that pressure change is a measurement of really what's happening with that pump. Now, we don't talk about it in terms of pressure, we talk about it in terms of head that the pump must deliver. So in order for us to calculate it, we can look at both sides of the system, the suction side and the discharge side. And the total dynamic head is the difference between the dynamic suction head, so what we're providing to the pump, and the dynamic discharge head, what the pump has to provide to make its way through the rest of the system. So total dynamic head is equal to dynamic discharge head minus dynamic suction head. Or if we have suction lift, we have the same idea. So dynamic or total dynamic head is going to be the difference between those two. Okay, so we've learned some terms relating to pumps and performances. So total discharge head, and then the components of that, the dynamic discharge head, the dynamic suction head, and some of the terms that go along with it. Pressure head, velocity head, and then previously our static head. In the next section, we'll do a couple of example problems on calculating different components within a pump system. So some of the terms and calculating the different quantities for them.